Chapter 4 Higher Order Differential Equations. In this video, we will discuss section 4.2 Reduction of Order. So, we will basically solve homogeneous linear second order differential equation by reduction of order. So, let's just recall the general solution of homogeneous linear second order differential equation is y equals c1y1 plus c2y2, where c1 and c2 are linearly independent sets of solution on some interval. And my homogeneous linear second order differential equation is this. Since the right part here you can see g of x is 0, so it is homogeneous, and it is linear because there is no product of y or y prime, and it only has a power 1. Its power is 1, or the degree is 1, and the coefficients here you can see these are just the function of x or constant. So it is homogeneous linear second order differential equation, and its solution is of this form. So reduction of order. So basically we will solve second order homogeneous linear ordinary differential equation, or you can say homogeneous linear second order differential equation. If the given solution, if there is a one given solution, okay, so for example here we have a reduction of order method. Given a solution y1, we want to find the general solution of this differential equation, which is homogeneous linear second order differential equation. Okay, so how we solve, what is the method of reduction of order to solve this differential equation? So here is the method. So we basically use the given solution y1 to find the another solution y2, so that we can get the general solution. So we assume that y2 equals u of x times y1 of x, where u of x is not a constant, it is a function of x. Okay, all right, so let's look at the method, right? So for, as I said earlier, we assume that y2 equals u of x times y1 of x. Here I just dropped that x variable. So y2 equals u times y1 be a second linearly independent solution of the DE. And the second step is then we compute y2 prime and y double prime. Since we said that this y2 is also the solution, so that means that should satisfy this differential equation. So we will substitute y2 prime, y2 and y2 double prime into the differential equation and simplify that. And the resulting simplified equation is linear in u prime or u double prime. And then or u double prime, or you can say just linear in u. And the next step is we will let w equals u prime to reduce the order of the differential equation, because our the method name is reduction of order, so here we will reduce the order by letting w equals u prime, and then we will solve the differential equation in w. And that differential equation, once we solve the differential equation, we will get the value of w, which is w equals u prime, and then we substitute w equals u prime, and then we will take antiderivative to find the value of u. So once we find the value of u, we will plug u equals here to get the value of y2. So once we get the value of y2, we will find the general solution, which is y equals c1 y1 plus c2 y2. So this is the method you have to remember. Alright, so let's look at some example by using reduction of method. Alright, so here we have a second order differential equation which is homogeneous linear second order differential equation. So we will solve this differential equation by reduction of order, since we are given one solution, y1 equals e to the x is a solution of that differential equation on the interval negative infinity to infinity. Okay, so let's just follow the method. So first step is let me change the color for just the solution. So let y2 equals u sub x times y1 of x, where u sub x is not a constant function. Okay, I will drop this x sign just to make calculation easy. I'm sorry, y1. Okay, and then take a derivative y2 prime equals, we need to use product rule on the right side. So the derivative of first, which is u prime, and keep the second as constant, plus keep the first as constant and take the derivative of second, which is y1 prime. And we also need to find y2 double prime. Again, use the product rule on the first term. So u double prime y1 plus u prime y1 prime plus, and I'm going to use product rule in this term, u prime times y1 prime plus u times y1 double prime. And we already know that y1 and y2, oh I'm sorry, y1, which we can plug it here, right? So instead to use y1, we can use that value. So I'm going to erase this one, and then let's just plug those values instead to use this one. Okay, sorry. So I already know that y2 is u times y1 is e to the x. This is the method. Okay, once you plug y1 values here, now find y2 prime, which is u prime e to the x plus u times e to the x. That's the derivative of e to the x. And then y2 double prime is, again here we need to use the product rule. So the derivative of first, which is u double prime, and keep the second as constant, plus, and then keep the first as constant, and the derivative of e to the x is just e to the x. And again we need to use product rule here, so it will be u prime e to the x plus u times e to the x. So you can see these two terms are similar, so we can add them. U double prime e to the x plus 2 u prime e to the x plus u e to the x, which is y2 double prime. So I'm going to plug these values into the given DE. So substitute in given DE. That's the second step. Let me go up here. Third step. First step is assume y2 equals u times y1, and then plug that y1 values and compute y2 prime, y2 double prime, and then substitute and simplify. Okay, so I'm going to substitute it into the given DE. So y2 double prime is this value, so I'm going to plug it into the given DE here. So it will be u double prime e to the x plus 2 u prime e to the x plus u e to the x minus y. We need to plug this y as y2. y2 is this value, so it will be u times e to the x equals 0, because y2 will satisfy the given DE. Okay, so let's see what terms are common. So this one and this one will be cancelled out, so we will have u double prime plus 2u prime times e to the x, since e to the x is common in both terms. Alright, now equals 0, I'm sorry, equals 0. Now once you plug these values, now you have to reduce the order of this differential equation, because the method is reduction of order, and that can be obtained by letting w equals u prime. So let w equals u prime, then w prime will be u double prime. So I'm going to plug these values into the above equation here. Substitute in star. So u double prime is w prime plus 2 u prime is just w times e to the x equals 0. And we know that e to the x is, we can divide both sides by e to the x, since e to the x is not 0. So we will only have w prime plus 2w equals 0. We can do this one. So you can see equation star was second order differential equation, but equation double star is first order differential equation, and because we reduce the order. Now we can solve this first order linear differential equation, right? So this is separable or first order linear differential equation. So you can use any method to solve this one. So I'm going to use first order linear method. So I'm going to find out integrating factor. So integrating factor would be e to the integration of 2 dx, which is e to the 2x. So this is the integration factor. Now I'm going to multiply this equation by integrating factor, and then it will be actually d over dx times w is the independent variable in this case, times in the integrating factor. I just escaped one step because we have already solved first order linear differential equation, so you might already know the method, that's why I escaped it. Now we are multiplying both sides by this, so 0 times e to the 2x is 0, just the 0. Now we will integrate on both sides, so integration with respect to x dx equals integration of 0 dx. So the integration would be on the left side w times e to the 2x, and on the right side integration of 0 is 0, 0 plus constant of integration, which is c1. Alright, now we can divide both sides by e to the 2x to get the value of w, which is c1 over e to the 2x, which can be written as e to the negative 2x. So that's the w. Now we need to return the value of w. So substitute back substitute. Our aim is to get the value of u. So once we get the value of u, we will substitute into y2. So w is u prime, which is equals c1 e to the negative 2x. I just plugged w equals u prime here. And let's integrate on both sides with respect to x to get the value of u dx. And the integration of u prime is u equals c1 is constant, so I'm taking out, and the integration of e to the negative 2x is over negative 2x plus another integration constant c2. Alright, so that's my u. You can choose c2 equals 0, or you can keep as it is, it doesn't matter. I'm just choosing, just to make it a little bit simple, choosing c2 equals 0, then and c1 equals negative 2, and then I will get u equals e to the negative 2x. So I'm plugging u equals e to the negative 2x into this equation to get the value of y2. So plug in y2 equals u times y1, which is y2 equals e to the negative 2x, and my y1 was e to the x. So it would be e to the negative x. So y2 is e to the negative x, right? So the general solution would be y equals c1. Because I have already used c1 and c2, so I'm going to use another constant c1 star y1 plus c2 star y2, and c1 star y1 is e to the x plus c2 star y2 is e to the negative x. So this is the general solution, but you can check whether these y1 and y2 are independent or not. So just to check independent solution or not, w of y1 y2, I'm finding the Wronskian function, which is y1 is e to the x, y2 is e to the negative x, and its derivative is e to the x and its derivative is negative e to the x. So I'm finding the determinant of this. It would be negative e to the 0 when you multiply this, and then minus e to the 0, which is negative 2, which is not equals 0. So the y1 and y2 are linearly independent, right? So this is the general solution of the given DE on the interval negative infinity to infinity. Okay, so this is how we solve the given differential or you can say homogeneous linear second order differential equation. Okay, so let's look at another example. Example number 2. Here it says that given y1 equals t is a solution of this homogeneous linear second order differential equation. So we will use reduction of order to find the solution, or another solution y2, and we will also construct general solution. Okay, so the first step, let y2 equals excuse me, u times y1, where u is actually u of x, which is not constant, and then I'm plugging this value y1 is t. So I'm going to find y2 prime, the derivative of first, keep the second as constant, plus keep the first as constant, take the derivative. So the derivative of t with respect to t is, oh, I'm sorry, here it should be a function of t instead of x. Excuse me. The derivative of t is 1. And y2 double prime is u double prime t plus u prime, the derivative of t is 1, plus u prime. So it would be u double prime t plus 2u prime, which is y2 double prime. And then since y2 is also solution of the given DE, so y2 will satisfy this DE. So I'm going to plug the value of y2 prime and y2 double prime into the given differential equation. So it will be t square times y2 double prime is u double prime t plus 2u prime plus 2t times y1 prime or y2 prime here will be u prime t plus u minus 2 times y. So in it we are plugging y2, which is u times t, equals 0. Alright, so let's just simplify it. It will be t square t cube u double prime t cube plus 2u prime t square plus 2u prime t square plus 2ut minus 2ut equals 0. So this will be cancelled out, and then here it will be u double prime t cube plus 4u prime t square equals 0. Okay, so let's just divide both sides by t cube. It will be u double prime plus 4 over t u prime equals 0. Okay, divide both side by t cube. Okay, so now you can see this is the second order linear differential equation. Now we will use the reduction of method. So we want to reduce the order of this differential equation. So let w equals u prime, then w prime will be u double prime. So I'm going to substitute it in star. So u double prime is w prime. So w prime plus 4 over t w equals 0, and this is we reduced order, and you can see this is first order linear differential equation, right? So we can find integrating factor. So integrating factor is e to the integration of 4 over t dt, which is integration of 4 times ln of absolute value of t, because the integration of 1 over t is natural log of absolute value of t, equals e to the natural log of absolute value of t to the 4, and absolute value of t to the 4 is always positive because of the even power. So, and e and ln are inverse of each other, so it will be t to the 4. So you can drop that absolute sign. Alright, so that's the integrating factor. So we will multiply equation double star by integrating factor to solve the linear first order linear differential equation. So multiply double star by integrating factor and do a little bit simplify. So I'm just writing directly. It will be d over dt of w times integrating factor, which is t to the 4, equals 0 times integrating factor, which is 0, and then I'm going to integrate both sides with respect to t on both sides. So on the left side it will be w times t to the 4 equals c1, constant of integration, and let's just substitute back the value of w, which is the u prime. So substitute back the w equal u prime, so it will be u prime times t to the 4 equals c1. So u prime will be c1 over t to the 4, so you can divide both sides by t to the 4, and this now you can find the value of u by integrating both sides with respect to t. So I'm integrating both sides with respect to t. So on the left side it will be just u, on the right side c1 times the integration of t to the 1 over t to the 4 will be t to the negative 3 over negative 3. You can use the power plus integration of constant. Now you can choose some values of constant so that you can so that y1 and y2 are independent. Here I'm not choosing right now, but we can choose it right. Okay, let's just find y2. y2 is u times y1, which is u is here, c1 t to the negative 3 over negative 3 plus c2 times y1. y1 was t, so I just plug it to get the value of y2. So I'm going to choose c2 equals 0. You can choose here directly but I just chose here. I just wanted to show you can choose anywhere. Now, so once you choose c2 equals 0, then it will be y2 equals negative c1 t to the negative 3 over negative 3. You can also choose c1 values, appropriate c1, but I'm keeping as it is. Now the general solution will be y equals c1 star y1 plus c2 star y2, and c1 star y1 is t plus c2 star negative c1 over, I'm sorry, we have a double negative sign here, over 3 t to the negative 3. You can just use one constant of integration. So c2 star times c1 is, you can choose c3, and then there is a negative sign, so I can drop this positive sign from here, negative t to the negative 3 over 3. So this is the general solution. Okay, all right, so let's do one more question. The method is same. So the given solution is y1 equals e to the negative 2t. We need to solve this differential equation. This is the homogeneous linear second order differential equation. Remember, we can use reduction of order method to solve the homogeneous linear second order differential equation. So here we are solving initial value problem this time. Again, the first step is assume that y2 equals u times y1, where u is use of t, because here you can see the t, so this is not constant. All right, so I'm going to plug the value of u1, which is e to the negative 2t, and then differentiate this to get the y2 prime, u prime e to the negative 2t plus, minus the derivative of e to the negative 2t is negative 2 times e to the negative 2t. y2 double prime is u double prime e to the negative 2t plus u prime, okay, we will have negative sign, so I'm just changing this negative to e to the negative t minus the derivative of this. Here we need to use product rule, 2 times u prime e to the negative 2t, negative negative will be positive, 4 u e to the negative 2t. Okay, and then this, let's just a little bit simplify it, negative 2t, and it will be negative 4 u prime e to the negative 2t plus 4 u e to the negative 2t. This is y2 double prime. So we are going to substitute the value of y2 double prime and y prime in the given DE. Substitute in the given DE. So y2 double prime is u double prime e to the negative 2t minus 4 u prime e to the negative 2t plus 4 u e to the negative 2t plus 4 times u, okay, 4 times y2 prime. y2 prime is u prime e to the negative 2t minus 2 u e to the negative 2t plus 4 y2, so it will be u times e to the negative 2t equals 0. Let's just simplify it. Okay, let's see whether there is any common. Okay, this one and this one, the first term will be cancelled out, and then u double prime e to the negative 2t plus 4 u e to the negative 2t. When I multiply this 4 with this 2, it will be negative 8 u e to the negative 2t plus 4 u e to the negative 2t equals 0. Oh, okay, we can see that this one plus this one is 8 u e to the negative 2t, and this is negative 8 u, so it will be cancelled out. These will be cancelled out, so we will only have e to the negative 2t equals 0. All right, okay, so since e to the negative 2t is not equals 0, so we can divide both sides by e to the negative 2t to get u double prime equals 0, or you can keep it as it is, or you can divide. Since e to the negative 2t not equals 0, so I'm dividing both sides by e to the negative t. So it will be u double prime equals 0. So now we need to reduce the order. So let w equals u prime. So w prime will be u double prime, and substitute in double star. So w prime will be 0. So integrate on both sides. We'll get w equals c1. All right, and then substitute back. W is u prime, so u prime equals c1, and then again integrate with respect to t. So we'll get u equals c1t plus c2, another constant of integration. So you can choose c2 equals 0 and c1 equals 1, then you'll get u equals t, and therefore you'll have y2 will be substitute in y2 equals u times y1. So your y2 will be u is t and y1 was e to the negative t. 2t. I'm sorry. So your y1 is e to the negative 2t and y2 is t times e to the negative 2t, which are linearly independent. You can check it. Thus the general solution of the DE would be C1. Okay, I'm not using C1 because we have already used C1 star y1 plus C2 star y2, and C1 star y1 is e to the negative 2t plus C2 star t times e to the negative 2t. But this is initial value problem, so we can find the constant, this the value of constant. So let's just use initial condition. Use the first initial condition is y at 0 equals 1. So I'm going to plug it into this equation. So it will be 1 equals C1 star. When you plug t equals 0, it will be e to the 0 plus C2 star times 0, because t is here, you are plugging t equals 0, so times 0, it will be 1 equals C1 star, because e to the 0 is 1. All right, C1 star is 1, so I'm going to plug in the triple star. So it will be y equals e to the negative 2t plus C2 star times t e to the negative 2t. Now we can find C2 star by using another initial condition. The next initial condition is this one. Okay, so use y prime at 0 equals negative 8. So that means we need to differentiate this one. So let's just say equation 1. So differentiate equation 1 with respect to t. It will be y prime equals derivative of e to the negative 2t is negative 2 e to the negative 2t plus, here we need to use product rule, so it will be C2 star e to the negative 2t minus C2 star t negative 2 e to the negative 2t, and then I'm going to plug these values. So y prime will be negative 8, negative 2 times e to the 0 plus C2 star e to the 0, and this term will be 0 since t is 0. Negative 8 equals negative 2 plus C2 star. So when you add 2 on both sides, then you'll get negative 6 on the left side, which is C2 star. Okay, so I'm going to plug that values here. It will be y equals e to the negative t minus 6t e to the negative 2t. So this is the general solution of the given initial value problem, and this defines on the interval negative infinity to infinity. All right, so that it is. Thank you.